Antarctica's icy border should be too hostile for life. Yet here, penguins plunge into water below freezing, and clouds of krill black out the sea. In these bitter depths, animals do not just survive. Something about this cold turns them into giants. Scientists now track megaswarms, record-breaking predators, and ancient adaptations. But the real question, how do Antarctic oceans make monsters the deeper you go, remains unsolved. The secret may be waiting just beneath the ice. At the edge of the Antarctic continent, emperor penguins gather in dense colonies, their bodies pressed together against the wind. The temperature hovers below freezing, yet these birds are preparing for a hunt that will take them beneath the ice into waters colder than the air above. When an emperor penguin dives, it enters a world where liquid water exists only because of salt and pressure, where the sea itself should freeze solid around living flesh. Still, the penguin's body is built for this impossible environment. Beneath thick plumage, emperor penguins carry a layer of fat that insulates against the cold. But survival demands more than insulation. Every cell in a penguin's body must resist the formation of ice crystals, crystals that can rupture membranes and end life in an instant. How do Antarctic creatures avoid freezing? Inside their blood, specialized proteins bind to the surfaces of forming ice, halting their growth. These ice-binding proteins and antifreeze proteins act as molecular shields. They latch on to the edges of microscopic ice, preventing crystals from expanding and piercing cell walls. This adaptation is not unique to penguins. Many Antarctic fish and invertebrates rely on similar molecular defenses. In the emperor, those defenses allow feats of endurance that defy expectation. Diving records show emperor penguins can reach depths of over 500 meters, holding their breath for more than 20 minutes. At these depths, the water temperature can drop below -1.8 degrees Celsius, a range where ordinary blood would begin to freeze. Yet the penguin's antifreeze proteins keep blood flowing, muscles moving, and the heart beating. Scientists studying emperor penguin physiology have traced these proteins to genetic adaptations shared with some Antarctic fish, suggesting a long evolutionary arms race against the cold. During each dive, the penguin's body shifts into a state of controlled efficiency. Blood flow to extremities slows, conserving core warmth. Oxygen is rationed, and energy is drawn from reserves built up during the brief Antarctic summer. Researchers tracking penguin colonies have documented how these birds time their dives with the rise and fall of krill swarms, using unique molecular defenses to hunt where few predators can follow. The cold is not just an obstacle. It is an active force, shaping every aspect of life in Antarctic waters. For the emperor penguin, evolution has turned the threat of freezing into a tool for survival, pushing the boundaries of what an animal can endure. As the colony returns to the surface, droplets freeze instantly on feathers, but inside, every cell remains liquid and alive. The line between life and ice is drawn at the molecular level. A pulse of movement ripples through the water beneath the Ross Sea ice, invisible to the eye but unmistakable on the ship's sonar. British Antarctic Survey researchers, hunched over glowing screens in the control room, watch as a living storm materializes, a megaswarm dense enough to register as a solid mass. In summer, these swarms can reach densities of more than 10,000 krill per cubic meter, stretching for kilometers in every direction. Each individual is no longer than a human thumb, yet together, their combined biomass outweighs the entire population of Antarctic predators that rely on them. Acoustic surveys reveal the true scale of these gatherings. Sonar pulses bounce off the swarm, returning signals that paint a picture of a churning, shifting cloud, sometimes so thick it blocks out the sea floor. In the Ross Sea, these living clouds are not a rare event. They are a seasonal certainty. As the Antarctic sun lingers on the horizon, phytoplankton blooms surge beneath the ice and feed the krill. The swarm responds, rising toward the surface in massive waves, then plunging deeper as the day fades. This vertical migration, tracked in real time by the survey crew, forms the heartbeat of the Southern Ocean. Net trawls confirm what the sonar suggests. The swarms are not uniform. In places, krill cluster so tightly that the nets come up brimming with life, while elsewhere the water is nearly empty. The largest swarms persist for weeks, even months, held together by invisible cues, light, temperature, and the chemical scent of food. British Antarctic survey researchers have documented swarms stretching for more than 100 kilometers, each one a mobile feast for predators. In these moments, the Ross Sea becomes an engine of energy, converting sunlight and phytoplankton into a living resource that will ripple through the food web. The energy stored in these krill clouds does more than feed penguins and seals. It sets the stage for everything that follows. The sheer concentration of biomass allows predators to grow larger, live longer, and venture deeper. Krill are not just prey, they are the foundation of Antarctic gigantism. Without these seasonal pulses, there would be no colossal squid, no giant amphipods, no deep-sea giants haunting the midnight zone. Every Antarctic animal that grows beyond the limits of its relatives elsewhere owes its size to the abundance and predictability of these swarms. For the survey crew, each pass of the sonar is a glimpse into the hidden machinery of the ocean. The data they collect, maps of swarm density and records of seasonal movement, will become the baseline for understanding how Antarctic giants begin. In the Ross, sea life builds upward from the smallest creatures, assembling the raw material for giants that will never see the sun. As the krill clouds drift and reform, the ocean itself becomes a living engine, driving the emergence of giants in the freezing dark below. The last rays of sun vanish beneath the ice, and the world below shifts from blue to black. In the Antarctic twilight zone, darkness is never absolute. Here, light has a new source and a new meaning. Giant jellyfish drift through the gloom, their bells stretching up to 2 meters across, living lanterns in the deep. Each pulse of their bodies sends ripples of faint blue and green through the water, a language written in flashes and glows. These jellyfish are not passive drifters. Lined along their tentacles and within the folds of their bells, specialized cells called photophores spark with chemical energy. Inside each photophore, luciferin molecules react with oxygen, catalyzed by the enzyme luciferase. The reaction is swift, releasing photons into the water. In this world, light is currency, a way to attract prey, confuse predators, or signal to others in the dark. Some pulses are slow and steady, a warning. Others flicker in code, unseen by human eyes but essential for survival. Remotely operated vehicles, guided by pilots on distant ships, have captured these displays for the first time. On their screens, the jellyfish appear as silent explosions of color, rings of light expanding and contracting with each movement. The pilots record the patterns, mapping the secret conversations of the deep. They watch as smaller creatures are drawn in by the glow, only to vanish as the jellyfish tentacles close around them. In Antarctic waters, the size of these medusae is as remarkable as their light. Bells span as wide as a person is tall. Tentacles trail behind like silk ribbons, some stretching for meters. The cold, oxygen-rich water allows these gelatinous giants to grow larger than their relatives in warmer seas. Their slow metabolism, driven by the near-freezing temperatures, means they can store energy from infrequent meals, using it to fuel the chemical reactions that power their bioluminescence. As the remotely operated vehicle lights fade, the jellyfish's own glow becomes the only illumination. In the Antarctic twilight, light is more than just a way to see. It is a form of survival. Every flash and shimmer marks a boundary between predator and prey, between the known and the hidden. In this silent ballet of light, the Antarctic giants reveal themselves only to those who know how to watch. In the Antarctic twilight, a new kind of invisibility takes hold. Some fish have evolved skins so dark it seems to erase them from existence. Ultra-blackness is not just a color, it is a strategy perfected in the arms race between predator and prey. In these depths, where bioluminescent flashes betray movement, any hint of reflected light can mean the difference between life and death. Optical biologists studying Antarctic fish have uncovered a secret hidden in their skin. Unlike ordinary dark pigments, ultra-black skin is built from layers of microscopic melanosomes, tiny pigment-filled organelles stacked and arranged to trap nearly every photon that strikes them. Instead of bouncing away, light is scattered and absorbed, ricocheting through a maze of pigment until almost nothing escapes. Laboratory measurements confirm the result. Over 99.5% of incoming light is absorbed, making these fish some of the darkest vertebrates on the planet. Melanosomes have become the invisible armor of the deep. This adaptation is not an accident. In a world where predators hunt by the faintest glow, the ability to vanish into shadow is a powerful defense. Lanternfish, hatchetfish, and other bioluminescent hunters sweep the water with their own chemical light, searching for silhouettes. Ultra-black fish turn this search against them. Their skin swallows the light, leaving no outline, no glimmer. Only the barest hint of movement might betray their presence, if anything at all. Vanish is their survival. The architecture of ultra-blackness is precise. Each melanosome is shaped and spaced to maximize destructive interference, a principle borrowed from the physics of stealth technology. Under the microscope, these structures resemble a forest of pillars, each one a trap for light. This design has evolved independently across multiple Antarctic and deep-sea fish families, evidence of the relentless pressure to remain unseen. Precise engineering at microscopic scale is what makes disappearance possible. In the Antarctic twilight zone, every adaptation is a counter-move. As bioluminescence sweeps the darkness, ultra-black skin answers with silence and shadow. The result is an evolutionary standoff, light against the perfect absence of light. For the fish that master this disappearing act, the ocean becomes a cloak. For predators, the hunt grows ever more uncertain as the line between life and the void blurs with each passing meter. Cloaked and unseen, these creatures rewrite the rules of pursuit and escape. Below the shifting ice of the Ross Sea, the Antarctic toothfish glides through water as dense with oxygen as any found on Earth. In these near-freezing depths, the sea itself becomes a resource, and life rearranges its possibilities around that abundance. Dissolved oxygen levels here reach nearly twice those of temperate seas, a chemical wealth that transforms what is possible into what actually exists. For a fish that can grow 2 meters long and weigh more than 150 kilograms, this invisible supply is the difference between thriving and shrinking. The result is not merely size, it is a kind of cold-driven gigantism. The physics is simple and it is profound. Cold water holds more oxygen. As temperatures drop, the solubility of oxygen rises, creating a liquid environment saturated with the gas every cell demands. That extra oxygen is the currency of life in these waters. The Antarctic toothfish is built to spend that currency. Its gills are broad and richly vascularized, drawing in oxygen at rates that would overwhelm the tissues of smaller, faster living fish. In the cold, the toothfish's metabolic rate slows, reducing demand while supply increases. The balance matters, because metabolic demand rises with body volume, while oxygen supply is limited by surface area. In warmer, less oxygen-rich seas, that equation sets a hard cap on how large a fish can grow. Here, the numbers tilt in favor of giants. Physiologists have mapped these relationships, measuring oxygen uptake and metabolic rates at temperatures hovering just below 0 degrees Celsius. The results are clear. Toothfish can sustain massive bodies because the water delivers more oxygen than their tissues can use, even at the slow pace of polar life. This surplus lets them grow slowly, over decades, and reach sizes impossible elsewhere. Their blood carries antifreeze proteins, molecular guardians against ice, but it is the oxygen-rich water that unlocks true gigantism. The Southern Ocean's chemistry sets the stage for an evolutionary experiment. What happens when the rules of supply and demand are rewritten? In Antarctica, the answer is measured not just in meters of length, but in the quiet persistence of life at the very edge of what is physically possible. As the toothfish swims through the darkness, every beat of its heart is powered by a chemical abundance few creatures ever know, making it both a survivor and a symbol of the deep ocean's hidden wealth. A Weddell seal exhales a burst of bubbles, then slips beneath the Antarctic ice, leaving the world of air behind. Ice cracks and silence answer the movement, and the surface becomes a distant memory. On the surface, scientists brace against the cold, tracking the seal's journey by faint satellite signals. Scientists watch, waiting, and they know that what disappears at the top can reappear in a place almost no human has seen. In these frigid waters, a mammal can vanish for over an hour, diving to depths near a kilometer, an endurance that defies expectation. Endurance like this reshapes how we imagine life at the edge of the world. The seal's body is engineered for this feat, a bridge between the oxygen-rich surface and the crushing pressure below. Engineered tissues, stored oxygen, and hardened nerves let it move where most animals cannot. Weddell seals are among the planet's deepest divers, with records of plunges lasting 82 minutes beyond 900 meters. These are the deepest journeys of any modern seal, a slow and precise descent into darkness. Each dive begins with a single measured breath. Instantly, the seal's heart rate plunges from over 100 beats per minute to fewer than 10 beats per minute. This bradycardia is deliberate, a controlled surrender of speed for efficiency. This dramatic bradycardia is no emergency. It is a strategy. Blood flow is rerouted to favor the brain and the heart, while the muscles draw on oxygen stored in myoglobin, a dense protein packed into their fibers. When oxygen becomes scarce, anaerobic metabolism takes over, letting the seal function even as available oxygen drops. Myoglobin and stored blood oxygen become the currency of survival. Researchers have followed these animals beneath the McMurdo sound ice using time-depth recorders to reveal a hidden world. Hidden features of the under-ice seascape only appear when a tagged animal wanders where no light can reach. At depth, the seal's lungs compress, reducing buoyancy and letting it glide with minimal effort. Body temperature drops, metabolism slows, and every cell conserves energy. Oxygen stored in blood and muscle is rationed with precision. This discipline allows the seal to hunt where few predators can reach, in the twilight zone where fish and invertebrates move sluggishly in the cold. Seals target dense prey fields, often the same krill-fed fish that sustain other Antarctic giants. A single foraging dive can reach 600 to 1,000 meters, with the seal navigating by sound and memory, mapping the under-ice world in search of energy-rich meals. Each successful hunt transfers oxygen gathered at the surface into the deep food web, fueling life far below the ice. For scientists, the Weddell seal is a living experiment in survival. Its ability to suppress its heartbeat, slow its metabolism, and thrive in near-freezing darkness reveals the radical adaptations that power the Antarctic ecosystem. Living proof that the Southern Ocean writes its own rules. On March 9, 2025, in the control room of the research vessel, silence settles as the ROV, Sebastian's camera, captures a shape drifting through the black water near the South Sandwich Islands. A juvenile colossal squid, 30 centimeters long, hovers at 600 meters. Its arms extend, eyes reflecting the ROV's lights, a living answer to a century of speculation. The crew leans in, watching tentacles flex and the animal's signature rotating hooks glint with each subtle movement. These hooks, found only in colossal squid, pivot on tiny joints, twisting and gripping with precision. Dr. Kat Bolstad, reviewing the live feed from New Zealand, confirms the identification as Mesonicoteuthis hamiltoni. The eyes command attention. Even in this young squid, each eye rivals a large coin, destined to reach nearly 27 centimeters across in adulthood. No other animal approaches this scale. Recent studies reveal the secret. The colossal squid's eye is a nearly perfect sphere, designed to capture the faintest bioluminescent glimmers in the deep. Its lens bends light from every direction, focusing scattered photons from distant flashes. Adaptations in the retina allow it to detect even brief flickers, signals from lanternfish or the approach of a sperm whale. Optical models show these eyes are tuned to the Antarctic twilight, where sunlight fades and bioluminescent signals travel far. Some tissue samples hint the colossal squid might produce its own light, photophores possibly embedded in the skin or arms, though this remains unconfirmed. If true, the squid could vanish or signal in the darkness, blending into a world of flashes and shadows. For the ROV crew, every detail matches predictions: the rotating hooks, the structure of the eyes, the shimmer of pigment along the mantle. The squid's presence at this depth and size confirms what scientists have theorized. Young squid live higher in the water, then descend as they grow, a living test of Bergman's rule. How large can these giants become? The biggest specimens found have weighed over 450 kilograms, with arms stretching beyond 10 meters. Yet no one has witnessed a fully grown colossal squid alive. This footage is only a glimpse, a fragment of a world where size and vision are shaped by cold and darkness. As the ROV's lights fade and the squid disappears, one question remains. In the Antarctic deep, how much larger do these giants grow, and what do they see that we never will? A single sea spider, legs outstretched, drifts across the Antarctic seafloor, its body barely larger than a coin, and its limbs spanning half a meter from tip to tip. These are pycnogonids, the sea spiders, and in the Southern Ocean, they become giants. Some recorded in recent years have reached leg spans of over 50 centimeters, dwarfing their temperate relatives 100 times. What force drives this transformation? The answer lies in the physics of cold water, the geometry of life, and the peculiar way these creatures breathe. Unlike insects or crustaceans, sea spiders have no gills, no lungs, and not even a heart strong enough to move blood through their entire bodies. Instead, oxygen seeps directly through their cuticle, diffusing across the thin walls of their legs. In most oceans, this method sets a hard limit on size, as an animal grows its volume, and thus its oxygen demand, faster than its surface area. But in Antarctic waters, the rules change. The cold holds more dissolved oxygen, saturating the water with the gas these creatures need. The slow pace of metabolism means their cells demand less energy and less oxygen over the long Antarctic night. In that quiet economy, life can be larger and live longer. Researchers studying pycnogonids have mapped this relationship. Surface area increases as the square of leg length, while volume, and thus oxygen need, rises with the cube. In warmer, less oxygen-rich seas, that mismatch would suffocate a giant. Here, the math that constrains size loosens. In the Southern Ocean, sea spiders can sprawl outward, their long legs becoming not just tools for walking, but living gills. Every square centimeter of cuticle becomes a portal for oxygen, every stride an act of breathing. Their legs are literally part of their respirations, thin walls exchanging gas with the frigid water. The largest Antarctic species, including Colossea, push this adaptation further than any other arthropod, their spindly frames maximizing surface area for gas exchange. They are built to be wide rather than bulky, a body plan that reads like a solution to a physical problem. Recent discoveries by British Antarctic survey teams, with sea spiders exceeding previous size records in the Weddell Sea and the Ross Sea, have reignited questions about the limits of this strategy. How large can a creature grow when its legs are its lungs? In the cold, oxygen-rich dark, the answer seems to be as large as the water allows. Here, the geometry of survival is written in flesh and chitin, each leg a testament to the strange mathematics of Antarctic gigantism. As a sea spider moves across the abyssal plain, it is both scavenger and pioneer, breathing through its limbs, thriving where others would suffocate. In these depths, size is not just competition or predation, but physics and possibility. The giants of the Antarctic are shaped by the cold, their bodies living proof that here the rules of life itself can be rewritten. A whale dies in the Southern Ocean, its massive body sinking through the water column, trailing a wake of silence. As it settles onto the abyssal plain, the darkness is absolute and the cold relentless. But this is not the end. This is the beginning of a transformation. Within hours, chemical signals from the decaying carcass drift on the currents, drawing in creatures from kilometers away. The first to arrive are the giants of the deep Antarctic isopods, armored scavengers nearly half a meter long, each one a relic of ancient seas. They converge in a slow-motion frenzy, dozens at first, then hundreds, crawling and burrowing through blubber and bone. Their bodies, pale and segmented, are built for these rare feasts. In the abyss, food is a lottery. Months, even years, may pass between meals. When a whale falls, it is an event that shapes generations. The isopods gorge until their bodies swell, storing energy in dense reserves of fat. Some may not eat again for years, surviving on what they consume in these brief, violent banquets. Survival is measured in endurance. Deep-sea ecologists have tracked the succession of life on a whale fall. The mobile scavenger phase can last for months, but the impact endures far longer. A single carcass can sustain a community for 5 years, supporting not just isopods, but amphipods, worms, and bacteria. Each stage brings new arrivals, each one adapted to a different window of opportunity. For the isopods, size is survival. The larger the animal, the more it can consume, and the longer it can wait for the next feast. In this world, gigantism is not a luxury. It is a strategy honed by the unpredictable rhythm of death and decay. In the Antarctic deep, a whale's end becomes a beginning, fueling giants that thrive on scarcity and endure in darkness. A plume of shimmering water rises from a crack in the Antarctic seafloor, carrying heat and minerals into the frozen dark. Around these hydrothermal vents, the rules of life are rewritten. Here, in the absence of sunlight, tube worms grow to lengths of 2 meters, their white plumes waving in chemical currents. These giants are not feeding on drifting plankton or scraps from above. Instead, their survival depends on a partnership with bacteria that live inside their tissues. The worms draw in hydrogen sulfide-rich water, deadly to most animals, and deliver it to colonies of symbiotic microbes housed within a specialized organ called the trophosome. The bacteria oxidize the sulfur, releasing energy that powers both themselves and their host. This chemosynthetic alliance turns poison into food, fueling growth in a place where photosynthesis is impossible. Biologists studying Antarctic vent fields have measured the chemistry of these oases. The water around the vents is rich in dissolved metals and sulfur compounds, and the temperature can spike to over 350 degrees Celsius just centimeters from the freezing abyss. Tube worms anchor themselves in mineral crusts, their bodies adapted to withstand both the heat of the vent and the crushing cold just beyond. Their tissues are lined with flexible proteins and pressure-resistant membranes, allowing them to thrive where few animals can even survive. Unlike surface giants, these worms owe their size not to oxygen or sunlight, but to the energy locked in the Earth's crust. The discovery of Antarctic tube worms has challenged old assumptions about where life can exist and how it can grow. Each vent is a chemical island, isolated and ephemeral, but while it lasts, it supports a community of giants, worms, clams, and blind shrimp, all living on energy drawn from the planet's interior. In these dark depths, the boundary between geology and biology blurs. The slow, patient lives of vent predators and scavengers begin here, where chemical energy births giants in the dark. A soft-bodied fish hovers above the silty floor, 5,000 meters beneath the Antarctic surface. This is the deep Antarctic snailfish, Filmed by remotely operated vehicle teams in 2023, one of the deepest living vertebrates ever recorded in these waters. Its body is almost translucent, lacking scales or a swim bladder. Instead, it is built from flexible cartilage and pressure-resistant tissues, adaptations that let it drift where the weight of the ocean would crush bone. Here, at pressures more than 500 times the pressure at the surface, the snailfish moves with careful, almost unhurried precision. Physiologists analyzing footage and tissue samples have found that Antarctic snailfish grow slowly, living decades in near-freezing darkness. Their metabolism is dialed down to its minimum setting, conserving energy in a world where food is rare. Each cell membrane is packed with polyunsaturated fats that remain fluid under immense pressure. The snailfish's entire body is a study in patience, slow growth, slow movement, and a lifespan that stretches longer than most surface fish ever experience. Further down the food chain, but no less remarkable, are the Antarctic sleeper sharks. These distant relatives of the Greenland shark glide through the abyss at a pace that barely registers. Radiocarbon dating of their eye lenses suggests a lifespan exceeding 400 years, an animal born before the Industrial Revolution and still living in the modern age. Growth rates are glacial, under 1 centimeter per year, but this slowness is a survival strategy. In the cold, oxygen-rich dark, every heartbeat is stretched, every breath a measured investment. Time itself becomes elastic in the Antarctic abyss. Creatures here are not just large, they are ancient. Their bodies are shaped by the physics of cold and pressure, but their true size is measured in centuries. For researchers watching the remotely operated vehicle feed, each encounter is a reminder. In the deep Antarctic, to be a giant is to live slowly, to endure, and to let time do the work of growth. 7,000 meters down, the South Sandwich Trench crushes water into a darkness. Few machines have ever entered. Here, the weight of the ocean stacks to more than 700 atmospheres, enough to crumple steel and enough to squeeze the life out of most creatures. Yet in this pressure-cooked silence, the largest crustaceans on record prowl the abyss, giants of the Antarctic deep sea. When the ROV lights sweep the trench floor, these scavengers appear as pale armored shapes, some stretching to 35 centimeters, longer than a dinner plate, 100 times the size of their shallow water cousins. The ROV team, hunched over monitors in the ship above, watches as amphipods swarm a patch of decaying flesh, likely the remains of a distant whale fall. Each amphipod moves with slow, deliberate purpose, their bodies built for survival in a world where the rules of biology bend under pressure. Their cell membranes are loaded with polyunsaturated fats, staying fluid and functional even as the crushing force of the trench tries to freeze and shatter them. Proteins inside their cells resist folding and breaking, stabilized by organic molecules that counteract the relentless squeeze. Pressure this extreme should limit life, but these amphipods have found ways to thrive. Their tissues flex instead of snapping. Their metabolism slows to a crawl, conserving every calorie. When food does arrive, a rare windfall in the trench, they gorge and store energy for the long famine ahead. Yet even these giants face a boundary. No amphipod has been found larger than 35 centimeters, not here or anywhere else. The question haunts the ROV crew. What stops them from growing bigger? The physics of pressure? The chemistry of their membranes? Or some unknown law of the deep? The South Sandwich Trench remains a place of unanswered questions. Each amphipod, each scavenger, is a living test of the limits of life in the Antarctic deep sea. As the ROV ascends, the team knows they have seen the edge of what is possible, but not the end. Somewhere below, in cold water, where Antarctic giants roam, the deep still keeps its secrets. What else lives in the trench, waiting to be discovered? Today, less than 1% of Antarctica's deep ocean has been explored by camera. As scientists capture new giants and stranger life each year, the boundaries of what is possible keep expanding. The greatest Antarctic predators and mysteries are likely still hidden in darkness. Thank you for venturing into the unknown with us, and please share your theories in the comments below. What new giants wait unseen beneath the ice?